So today we will do some kind of a case study. Where we will take some a few examples, okay, with respect to like I have targeted few examples, one with respect to nvme, ext3, and kernel loop, so that we get to know how it has been detected and how it has been handled. Okay, so that's the goal of this case study exercises what we will be doing today. Okay, so I think already I've already stressed to some of you people. So basically, like if you want to look into any of the kernel bugs, right, even you can look at the old bugs also. Okay, not just the recent bugs. You can go to like bugzilla.kernel.org. You'll find all the bugs that has been opened with respect to the kernel at any point of time. So some will be closed and some will be open at any point of time. For example, whatever we are looking at is the resolved bugs, which is resolved and then it's been closed basically. Okay, so that is a kind of bug which we are targeting. Okay, so for example, if you look at one of the issues, what we will be targeting today is something to do with nvme. First we will try to understand what is nvme and all about that. Okay, so in this, what this comes under a storage category. So this is a block driver. Okay, nvme is a block driver, so which is meant for storing the data, something like your SATA or other things. So we will try to understand that first. So in this, what had happened was basically in the 2020, right? So basically in the kernel version 5.78, the issue was detected. For example, with a specific drive, okay, from Silicon Motion, right? In this particular drive, it was seen that the kernel used to crash. So that was detected, and basically it was not detecting, or it was not working fine. So the thing was, there was there was an mechanism where this issue was identified. So and then they wanted to fix this issue. That is how it went about. Okay, so now before going to this, and as we already know, right, so anybody can report the issue into this Bugzilla. For example, even you can also do it. So while you're testing anything, okay, any Linux kernel issue, and you find that is not behaving as per your expectation, you can raise a bug here. Okay, so what will happen is all the bug that has been raised in kernel.org, what will happen is it will be taken care by the kernel community. They'll have a look at it, and if they feel it's a valid bug, then they will take it up for fixing it. Okay, or else, so basically what will happen is they will try to detect which category or which module this bug will arise from, and after that there'll be this bug will be assigned to the corresponding module owners. So the module owners will have a look at it and try to fix the issue. In case this bug hasn't already been fixed, then what they will do is they'll give a link to this whatever mailing list where the bug has been already fixed. So what they will do is they will provide a link to the issue which has already been fixed, so that people can have a look at it and they can go ahead with respect to that. Okay, so that is one thing they will do periodically. Okay, for example, for this issue, right, this didn't take much of information, so they had a look at it and they found out that this bug is already fixed, and they gave a link to the patch which was merged at some particular point of time. Okay, and so this is how it happened in this particular bug. If you look at this bug, right, which is related to ext3, basically there was a memory leak. It was arised in 2.6 2.6 kernel, okay, which has been closed also. So in this particular bug, this was not straightforward. Actually, it was reported, and then to get more and more details about the issue, lot of information was attached to this archive, to so that it becomes a module owner or the people who are working on the bug becomes more easier to reproduce and try to understand what the issue is all about. That is one of the things that you can see in this particular scenario. Okay, so now you can see that a lot of data was attached, like slab info, mem info, and slab top outputs, the mount output, the dmessage output, a lot of things. And after, and even the kernel configuration was also passed with respect, and this bug was arising with respect to ext3. So all the parameters was given so that it becomes easier to reproduce. So after reproducing, a fix was given by a corresponding module owner. Okay, so which I'll be showing down the line. Okay, so it was fixed and the issue was closed. Okay, so this is one sequence of the bug what you can see here. The other one is related to ext3 file system itself, where under a certain scenario it was seen that it used to crash basically. Okay, so the crash used to occur, when you are running f-stress utility. The f-stress utility is a file system stress utility where you can stress your file system and perform lot of actions over it. So when you're running the f-stress utility, because this utility itself is meant to stress the file system to the extreme conditions. Okay. So under such condition, it was found that your ext3 file system used to crash, and it was identified via the call stack. So we will try to go through that and try to understand what does it mean. And if you see here, the call stack clearly indicates that it's something to do with file system. And it happens when you are running with respect to f-stress. So because of this reason, the bug was reported. See, the thing is, we can run any utility or any kind of other mechanism in the application space, but that should not lead to any crash in the kernel space. That is one thing what we should always remember. Okay, if that occurs, that's an indication telling that something has not been handled correctly inside the kernel, because this is an application program, okay, which is meant to stress your file system, and that is leading to a crash inside the kernel file system code. So this is not correct. So that is the reason it was reported immediately. So after it was reported, and over the time, it was fixed in, for example, 2.6.9 mm2, and then that was tested and it was verified and it was closed by this particular tester. Okay, so because he was the one, so it was tested by some author and it was closed and it has been fixed. So this is the reporting guy. So normally what will happen is the reporting guy can also test it and he can close it. That is also possible. Or some other tester also will verify it and close the archive, telling that this issue doesn't exist anymore. Okay. So this also can be done. Okay. So what I'm trying to tell is this is how the sequence of bug flow will go about. If you want to find more and more information about it, you can just look at it. There will be a lot of bugs still open at this particular point of time also. Okay, let me show that actually. You can search. There will be a lot of issues that is pending. You can find anything. Okay, so you can put any part. For example, if you want to find out any issues with respect to ext4 or something like that, basically. Okay, so let us assume, let us see if there is any issues that is reported with respect to ext4. Yes, for example, if you see here, right, this is issue which was reported and still it is in the open state only. It is not fixed yet, where USB HD, so it's something to do with ext4 file system. And there is a kernel branding when you are booting the kernel. This is also still in the new state. It has not been assigned to anybody, and then it is not fixed. The bug sequence flow is something like this. When you create an archive, it will be in the new state, and then it will go to the assigned state. And then after that, once it is assigned, when somebody fixed, it will go to the resolved state. Once it has been fully tested, then it will be closed. Okay. So like that, you can see a lot of issues that is arising here. So what you can do is like that, you can check, and if you want to work on any archive, you can also take up and work on any archive. That is also possible. Okay. So now let us try to understand about this NVMe subsystem, what it is. So as I told you, this is a block driver. Okay. So before going through this, let us try to understand what is this NVMe drive all about, and what is the purpose of this NVMe subsystem, so that we know what are we talking about. Because the reason is in this case study, right, I thought of explaining you about some new protocol also about NVMe. So that's the goal of this. Okay. So let us try to understand what is this NVMe all about. So now what we will do is we will try to understand about this NVMe subsystem first. Okay. So if you check out first, as you see here, NVMe is nothing but a new protocol that was introduced recently for your block drivers. It's a replacement of your normal drives, right? For example, previously, if you remember, there are a lot of storage media that came up, and previously it was a lot of storage media was mechanical in nature. Okay, so it used to be like, for example, hard disk and other things. Initially you had a floppy disk, then you got into something called CD-ROM drives, and then later it entered into hard disk. Okay, which was a mechanical in nature, and after that people started moving to NAND drives. So basically your SSDs. Okay, so NVMe is one kind of SSD drive. Even in NVMe, there are a lot of protocol that will exist. One is called as SATA protocol. Okay, so which is called a serial ATA. So, okay, so the NVMe Express is a different protocol compared to your SATA, which is working towards getting the better throughput. So we will try to understand that. So you take any drives, right? There'll be a medium of connecting this particular, if you take any drives, right, it will be split up into following layers. First is a transport layer. So what transport layer that is required for connecting to this particular drives? Okay, so NVMe Express drive, which is also called as non-volatile express drives, the main media of connecting this particular drive is nothing but your PCIe subsystem. Okay, so this connects via this particular drive is connected via your PCIe subsystem. That is something which you need to understand. Okay, so if you, for example, if you see here, right, can just show you if it is not here. Let me check out. Okay, so it is not installed on the subsystem. That is fine. So normally, just give me a second. So there is a command. Yeah, I can just show you here only. Okay, so if you, there is a command called sudo nvme list, and if you look at it, right, you will get a output just similar something like this, which will indicate that there is a non-volatile memory controller, that is nothing but your nvme controller of some particular type, and this will be listed in your PCIe list. Okay, so in your PCI list, you will see this particular device indicating that a particular NVMe drive has been connected to your subsystem. Okay, so the transport layer that has been used for this NVMe controller is nothing but your PCIe. So this PCIe is connected via this NVMe via your PCIe transport layer. That is something which you need to understand. Okay, so then I think all of these things you will know how this commands and how to use these commands, and basically if you want to figure out and see if the NVMe controller is listed, right, you have to run all of this command. Since I think most of you know how to run this command, I will not go into this command. Okay, so you know basically how to see the life. So basically what I meant is once you run this LSPCR, right, you should be able to see an NVMe controller listed on your subsystem. So you will get to know that the NVMe subsystem is active. So let me see if I can turn on here. Just give me a second. So let me see if I can add one. Okay, if possible. You can add this if you want to simulate, right? You can add one also. So if I can add hard disk, you can add one hard disk. Yeah, there will be a lot of drives. Okay, fine. So NVMe is not possible. Okay, so I need to power off to add NVMe. So basically, you will see a lot of these drive categories. One is your IDE drive. All your hard disk previously was based on IDE, and it also was based on CUSI. Okay, now you have something called a SATA and NVMe. So these are the different kind of disk category that can exist. It can come in any of these three categories. Okay, so now, so one thing is you have to run your NVMe subsystem. Just a second. Yeah, fine. Yeah. So one thing what you have to do is you have to run this command just to see that NVMe controller is there in the list. That is very important. Okay. So once you see that NVMe controller is there in the list, just to show that okay, your NVMe drive has been detected. Okay. So if you remember, right, so the class of that particular subsystem will come under a storage class, which is nothing but an NVMe storage controller only. Okay. So that I think you will all know how to do it. So I will not go into that. Okay. So now one thing what I want to understand is your storage architecture. So for example, if you take any storage subsystem, right? So it will be it will have following parts. It depends how is your storage media. Means how are you storing the data on your subsystem? Okay. And the next thing is what is your transport layer? Means whenever you want to transfer the data from your application to the disk, how are you going to transfer it? What is the media you're using to transfer the data? And next thing is you'll have something called as a control layer, which will control this subsystem. How are you going to control this subsystem? That is what will be indicated. That will come as a part of the control layer. For example, if you talk about SATA, ATA, PCI, right? What does it indicate? That is what I want to highlight here. And the next thing is whenever you want to issue a command to this particular drive, how are you going to issue the command? So based on that, there'll be a lot of standards. So based on this, there is 3 standards that is available. One is called CUSI, your ATA, and your PCIe subsystem. So these are the following medium that can exist. Okay. So now, if you want to send any commands, either you will send a CUSI command, ATA command, or NVMe command. For example, if you are talking about NVMe drives, you'll be using, there is an NVMe command that is possible, and you can also there is also NVMe control layer that is available. Okay. But once you come to the CUSI drive, you'll have a CUSI command layer only. But in the ATA drive, basically your SATA drives, the command can be of 2 types. You can pass an ext3 command to the SATA drive, or you can pass an ATA command to your SATA drive. Means that whenever you want to communicate with the SATA drive, you can issue the command, you can control it via the ATA protocol or ext3 protocol. That is an indication. Even though the high level command layer is of type ATA, but control layer can translate either to the ATA or HCI. Okay, so if you remember, you might come across this term called HCI and other things, but basically the drives are classified into three types: the CUSI, ATA, and PCI. These are the main three categories. Okay, so the transport layer varies here. For example, CUSI, for example, your USB, right, still works using CUSI protocol only. They are fully followed and based on CUSI layer. And even your hard disk, all your standard hard disk, whatever you talk about, okay, so 2.5-inch hard disk or whatever hard disk you talk about, the magnetic hard disk, all of those works use your CUSI protocol only, CUSI standards only. Okay, and in that cases, the storage can be anything. For example, if you take an USB, the storage is the NAND flash. The inside the USB there will be a NAND flash, but the protocol what it will be supporting is your CUSI protocol. And for example, if you take your HDD or any of the magnetic disk, okay, 1 minute. Yeah, you take any of the magnetic disk, that also in that particular scenario also the storage layer will be based on your it will be either magnetic disk, or it can be based on magnetic disk, or it can be based on NAND flash also, as we see in the USB case. Okay, for example, if you remember, there are a lot of SSD based on SATA. We call it as a SATA SSDs. For example, let me show you that. Just give me a second. Okay, and they'll have a different connection also. It will not, you can't connect them directly. There'll be a different SATA ports. Okay, you have to connect them on that particular SATA ports only. Okay, so these are all the many SATA drives that is available. So if you want to see the interface, right, how it will look like, I will just show you that. Just give me a second. Yeah, you will have the SATA cable. I think you people would have seen something like this cable. Okay, your output will look something like this. As you see here, right, there will be some data lines and there will be some power lines. So you will take this particular lines and then you will connect to one part to the power and other part to the data lines. Okay, so then you will have the SATA drive up and ready, as you see in this particular scenario. It can be either this, or if you see raw with all the what you casing removed, it will look something like this, as you see here. But ultimately, at any point of time, it will be visible something like this particular point. So the connection point will be something like this. One will be for the power, and other one will be for the data. So this something like this. So casing is same, but always the output will be something similar. So one is meant for data, and other one is meant for the power. So you'll connect the power line to your PC power connection, and other one to the data, so normal SATA the connection point. That is what you will be doing at the most of the scenarios. Okay, so it will also come in multiple form factors and other things. So this is the normal SATA case. Okay, so it will also come something like this also. You will have some connections, something like this. I will explain you at the later point of time. This is how it will look. Okay, so if you take any of the SATA drives also, so what I want to stress here is that this SATA whatever SATA drives we are talking about, either it can work by the PATA protocol, or it can the transport layer can be PATA, that is nothing but parallel ATA, or it can be based on serial ATA, one of the things. Okay, so then you would have one more category called your nvme drives. Okay, so if you look at the nvme SSDs, it looks something like this. Yeah, so this is your nvme SSDs, and this is how it will look like. It will come in multiple form factors. I will explain you all those things. What does it mean? It will be something like this. Okay, so there will be few lines which is meant for data, and few lines which will connect to the PCIe slot. Okay, so this data, some of the data lines will plug into the PCI. These are all the PCI subsystem. Okay, so it can connect into PCIe into 1, into 2, or it can be anything. So it can connect into PCIe, any of the PCI slot. It depends actually. Okay, it can connect into 4 or into 1 or whatever it is. So if it is into 1, you'll be able to expand, get only into 1 speeds, or you can get more speeds also. There are a lot of variants of SATA drive, but your normal normal NVMe drives will look something like this. Okay, and the main thing what you need to understand is the transport layer, which will transport the data, is done by your NVMe subsystem. That is something which you need to understand. So since it works on the NVMe subsystem, right, the transfer rates are very high, and you will get a very better throughput. And it also has a lot of the architecture itself has a lot of other advantages, which we'll see down the line. But one of the main thing is that since it connects to PCIe, you will get almost same throughput as you want to get via the PCI. So it can go, some of the NVMe drives you can get a throughput up to 20 Gbps also, or more than that also. Okay, so this is the kind of throughput and speed what you will get from the NVMe subsystem. So what I'm trying to stress here is these are the different standards that is available. Okay, so you'll so these are the things. So SCI is your normal serial what do you tell, computer system interface, which all this hard disk and USB and other things are available, and till now your USB also works using this storage standard called CUSI. Okay, so and you have another standard called ATA. So there also you will try to connect. Okay, so and then after that there is one more architecture that is nothing but NVMe architecture, which is connects to the PCIe subsystem. So we will understand how does it work. So first thing what I want to explain here is there are three storage models that is available: CUSI, ATA, and NVMe. This is the main things what you want to understand. Okay, so now what will happen is that based on CUSI and other things, there'll be way how the command will be passed. You can look at all those things. That's fine. Okay, so I will not stress much here because it's a very standard thing. Okay, so what will happen is when see normally whenever you send the command, right, as per the standard, there'll be a format how to push the command and what response you want to get. Okay, so based on that, you will get the response and you can use it for your controlling. For example, even you have your ATA, you will get your ATA data sheets also. Standard ATA data sheets, okay, which tell how the command should look like, how it should communicate. Command specification. There are an ATA command specification. You can look at it. This will give a complete information telling that what are the basic command set a particular SATA subsystem, basically your SATA subsystem should support. So whenever you tell we support an ATA standard, we should support this standard. There's a standard specification. For example, if I tell I'm complying to SATA, so what should I support? So there is a standard specification which tells that what kind of commands you need to support, what kind of feature set you need to support. Okay, so what kind of register set you should have, and how you should able to access, how to handle the other entities. So there is a big list. Okay, so you have to support all of this feature set to make yourself compliable along as per this particular drive subsystem. Okay, so this is something which you can have a look. So whenever you tell CUSI specification, there is a specification even for that also, which talks about, yeah, for example, this is for CUSI. For example, if I tell my drive is compliant with CUSI, right? So what and all it should support, and what feature set it should support. If I send some particular command, how it should respond, how it should behave. So all those things has been mentioned here. For example, if I want to read, what should I do? Well, there is one read command 6, read command 10, read command 12. So like this, there are a lot of read command. If I want to do a buffer read, like this, there are a lot of things that this particular drive supports. Okay, so this is what internally your USB supports most of the times. Okay, so there is a standard specification telling that if I want to follow this particular storage mechanism, what should I do? Okay, so like this, there is a specification even for your NVMe subsystem also, how it should behave. So if you look at this NVMe specification, there are a lot of specification that is available. All the specification is available in your NVMe Express site. You can have a look at it. This also tells basically, okay, how your system should look like. Okay, so why I'm stressing on this is, for example, if you want to fix any of this RQ, right, it's better to understand internals of it, what it is and how to work. So that is the reason I'm telling. For example, if you go to this NVMe interface, NVMe specifications, right, this is for each developer whenever you want to develop any driver. Okay, it could be driver, or if you want to develop the drive itself, the drive hardware itself based on this protocol, how it should support, what it should support. So all those things is available here. You can see all the things. There is a lot of standards that is available. It started with the standard 1.0, and you can see that currently the base specification that is available is 20.b. So you can look at it. It gives the complete information, like what all feature set you have to support. Okay, so when I tell myself I have compliant to NVMe 2.0 specification, right, it means that I'm supporting all of these features. So there is a feature telling that what all commands you need to support, how to do it, and what all actions should I do when I power on, how I should behave. So there is a complete feature set that is available. Okay, so and I will explain you some commands also. So this is what it is and what register sets are available, how it is available. Everything will be mentioned in a specific thing. So what I'm trying to stress here is, whenever you talk about any storage architecture, right? So as I stressed before, there'll be of only three types. Okay, so either it will be CUSI, ATA, or PCI. These are the main things. And all the specification is what, as per whatever I have mentioned here. You can have a look at it. If you want, I can pass a link to you. You can look at it basically. If you want to go in depth and understand what are all these commands and other things, right? You can find all of this information in this particular parts, which will tell how we should form the command and what way you have to form the command. So everything, it will be mentioned in this particular scenario. Okay, that is very important. Yeah. So now, for example, whenever I want to communicate with any CUSI device, right, you should have a CUSI controller. Okay. So for example, whenever I want to communicate with any ATA subsystem, you should have an ATA controller. Or similarly, whenever you want to communicate by NVMe, you should have an NVMe controller. Okay. So that is all the important parts that is required. Okay. But the advantage of NVMe is different. For example, in this, you should have an ATA controller on your processor. You should have a CUSI controller on your processor. But here you need not have anything here. Okay. So I will explain why it is not required when I mention down, because the reason is, till now the architecture was something like this. You'll have a main controller on the PC side. Okay, wait 1 minute. Let me put a proper text. So you'll have a main controller. So it could be anything. You'll have a main controller here, and other end you'll have a device. So for example, you have a CUSI device at this end, and that will connect to the processor, and that processor, via the signal, it will connect to the controller, and controller will communicate with the device and get the information. But NVMe subsystem itself is entirely different. So whenever you connect your NVMe subsystem, right, so the NVMe device itself will have a controller, and that will connect to your PCI subsystem. So it's like a board which has both controller and device on the same particular entity. So what will happen in this is, you'll have a controller plus NVMe drive basically on the same particular subsystem only. So what will happen is, if you remember, right, whenever I connect any entity to the PCI subsystem, right, there'll be kind of an handshake that occurs between both of them, where you will try to get all the capability, like you will get a vendor ID, product ID, and other information with respect to the PCI subsystem. And based on that, and even you will also get a class information. Based on that, you will find out what it is. And before that, the memory mapping that occurs, the register set of that particular device will get mapped into certain, because a memory will get allocated for the register set. Okay, and a register set will be available, and you will have a memory for storing the information, and you'll have some section of memory reserved to access the register set also. So the moment I have an access to the register set, right, I can communicate with the controller and issue the command the way I want. Okay, so that is the reason you'll have a controller plus device combined on the NVMe drive itself, basically. Okay, it has a combination of controller plus device that is available. So that is the reason it's bit compact, and you don't see anything available on this. It's something like, for example, if you take a GPIO card, let us assume that you want to connect, you have a PCIe GPU card, okay, graphics card which you want to connect, right? You will have a GPU controller, and that will also it will process all the GPU data, and then it will also control your basically your display also. You will have a display out. Moment you connect to the display, the output will go to the display also. Okay, so something like that. This particular NVMe controller will have NVMe drive will also have an NVMe controller plus the storage subsystem on the same particular storage media. Okay, so that is something which I want to stress here. Okay, so now if you look at it, as I told you, it contains all this NVMe subsystem. Okay, so now one important thing is, for example, if you have any HCI subsystem, right, and if you want to push any command, okay, so if you want to push any command, right, for example, you will have a processor memory complex, okay, which is connected via PCI, and other end you will have an EHCI. Okay, so then you will have an EHCI HBA. What will transfer your EHCI to your SATA. Okay, so you'll have something called as an advanced host controller interface that is available on your chip, that will be used to communicate your SATA subsystem. So what it will do is, it will translate the command what the user has to send to the SATA subsystem, and it will communicate with all the SATA address. This is how your normal SATA communication would look like. Okay, so that is one thing, and this was the EHCI was the standard that was used for a pretty long time. Okay, so if you look at any storage subsystem, till now it was based on EHCI. Okay, so now if you look at your NVMe, right, your NVMe subsystem is fully as it has its own protocol. Okay, it is different from your EHCI. So one of the main difference between your NVMe and EHCI is, I will tell you one thing. Assume that let me give one example. Okay, you have your storage media here, and you want to perform some operation. For example, if you see the specification of your SATA or PATA or whatever it is, right? And even your other EHCA specification and other thing, whatever SCSI specification, right? What we saw was there are multiple commands to perform specific action. Now let us assume that there'll be hundreds of applications which are trying to access the same media. Let us assume one of the application will trigger one command to read the data. One more application will trigger a command to write the data. One more application will trigger to delete some other data, and one more application will do some other action on this particular subsystem. Then what will happen is all this command will come here, and this command will be pushed into some. In this controller will have one queue to process all the command. Even though the command comes in parallelly, this will be queued inside your queue. That is nothing, what we call it as a command queue. Okay, and there is also a limit telling that how many commands it can be queued on this particular, because there is a limit. It doesn't mean that I can put an infinite command on this queue. There's a limit because it's ultimately a memory subsystem, right? You should have a capability to store specific number of commands. So there'll be a limit. How many command queues, how many queues I have, and how many commands I can put in that queue. If you take your old HCA subsystem, which has been used till now also, it will have only one command queue. Means that when a lot of application wants to push the command, all the things will go in one command queue. As you see in this particular example, it will go in one command queue, and each command queue can have only 32 commands. As you see in this particular example. Okay, so you'll have one command queue, and each command queue can hold 32 commands. This is where the NVMe will come into the picture. If you look at it, NVMe can have 64K queues. Means you can have 64 such queues. Okay, so each NVMe subsystem can have 64K queues. Means that you need not put a lot of commands on a single queue, and all of them will be processed parallelly. For example, if I put 111 command in all the queues, all will be processed parallelly and simultaneously. That is how your NVMe subsystem will work. So instead of putting all the commands in one single queue, I can put one command here, one command here, one command here in other queue, so that all will get executed in one shot. So like that, I will get more and more performance. That is the advantage of your NVMe drives. That is the reason NVMe drives, whatever you see today, are very powerful. And one more thing, to add to this more complexity to this, each queue can support 64K commands. Means it's not that you can put commands into 64 queues. Each queues will support 64K commands. Means if you look at the capability of maximum command handling capability of this NVMe drive at any point, so at one shot you can handle 64K commands. That is one thing. And after that, total commands, what it can be store at one shot. It's nothing but in 64K into 64K. So much commands you can store at one shot. That is the capability of your NVMe subsystem compared to your old classic EHCA subsystem. If you look at old EHCA subsystem, you can only execute one command at a time. But here you can execute more commands since you are more queues. And at a max, you can store only 32 commands. Means that your EHCA subsystem can only maximum execute 32 commands. For example, if I want to transfer some data at very fast rate, if the data rate, for example, let us assume that to put 32 commands to the queue, it will take 3 minutes or something like that, I will assume. And to execute each command will take some X amount of time. Then I have to wait for one command to complete. Once the queue is full, right, I have to wait till a command is executed and I have a free space so that I can add one more command. Okay, so this is something which I will be able to do in this subsystem. Okay, so this is something which I'll be able to achieve with respect to this NVMe subsystem. So that is the reason NVMe subsystem is very popular, and we will try to understand that also. Okay, and one more thing is, if you look at it, there is also how much commands you can access at how many registers you can access at a time. Okay, how much time you need to access the registers, that you can check out here. For example, in this particular entity, right, you need almost 6 to 9 queue command cycles you need to access, but here you will happen in only two commands, right? You'll be able to access, and this will support only one interrupt. So means that, for example, if you have one HCI command, right? If you want to process something, it will trigger only one interrupt. Here, it can support 2048 MSIX interrupt. That is nothing but a software interrupt that is available. So using this, you can generate 2K interrupt at one shot. Means that if I want to, let us assume that I have more queues, I want to process a lot of things at one shot in parallelly. So I can do that because I get more and more interrupt which is associated to different things. Like that also I'll be able to add it. Okay. And next thing is, as I told you, since there is a limit here on the queue and the number of commands, right? I need a lot of locking with respect to HCI, else it will not be possible to handle it. Here I don't need no locking because there is so much of queues, and each queue can support so much of commands. So means that if I have 4 threads, I will associate 4 threads to different queues. So that what will happen is each thread will be writing data at a different queues, and one command, one thread will not affect the other thread command because it's using a different queue and they're working. So because of which you don't need any locking also, which will increase the efficiency. Okay, so that is one thing, and the data transmission is full duplex, and you can transmit and receive at one shot. For example, since it is a single command queue, right? If I want to transmit the data, I have to put a receive command in the same queue. So only after the transmission, I will get the receive command executed. So it's a half duplex operation. Only after transmit, I'll get the received data back. But in nvme, right, since I have a multiple queue, right, and it also gets executed parallelly, in one queue I can put a transmit command, in other queue I can put a receive command. So I can perform both transmit and receive in a single operation. It's something like a full duplex operation. I need not wait for the transmit to complete, one command to complete. After that, I need not execute another command. So that is the reason this makes nvme more popular in the existing world. Okay, so that is one of the thing what you need to understand. And if you look at the eye level picture, right, your NVMe drive, right, ultimately what will happen is NVMe subsystem is fully based on your NUMA architecture. Okay, so and it will always connect your PCIe subsystem. So what will happen is if you will connect your NVMe SSDs via PCIe. And once you connect it, you can directly access it. For example, if you want to connect your SATA drives, right, you should have your HBA block. For example, if you see, right, we had an HBA block here. This is your HBA subsystem, which will translate to HCI to something else. You need a translator because all the commands that your processor can understand your HCI command, that will be translated to your SATA or something else, and from that it will come into your drive. So it's a long pending process. But if you look at the NVMe subsystem, right, the NVMe drive is directly connected to the CPU via the PCI subsystem. So using which you can access your NVMe subsystem, you can transmit and receive the data at very fast rate, as you see in this particular example. It is not that you should go to HBA, you need to translate, then after that you have to go to SSDs and perform the translation. You need not do all those things. So that is one of the main advantage. And one more thing, since it uses PCI subsystem, right? PCI has lot of commands that is available to perform dynamic translation also. For example, if you want to transfer data from the RAM to the SSDs and SSD to the RAM, dynamic memory access, all those things are possible easily with respect to your NVMe. So this is how your NVMe block structure would look like. Okay, there will be data layer, transaction layer, and it will have an application layer at a same like your networking stack, right? It will have different layers. And basically the NVMe subsystem was triggered and it is maintained and it is run by this main 13 companies. They promote the specification, they improve the specification, and they push the specification. Okay, that is what you're seeing in this particular list here. For example, Marvell, Micron, EMC Square, Cisco. So these are all those, even your Intel and Samsung and LSI. So these are the main 13 companies which are responsible for pushing the specification, and they will also try to see how we can improve this over the time. So that is one of the things what you need to understand. So there are a lot of things how the data transaction really occurs. And if you look at it, NVMe is classified into a lot of form factors. I just want to explain this also, it will be useful. There is a lot of form factor. One is called U.2 form factor. There is something called M.2 form factor. In M.2 also there are multiple form factor like type 2 and type B. Okay. So for example, let me show you this U.2 NVMe, how it will look like. Yeah. So your U.2 NVMe will look something like this. This is your U.2 NVMe. It will look something like this. Okay. So if you look at M.2 NVMe, this is another form factor. Yeah, it'll look something like this. Okay, so your m dot to nvme will look something like this. As you see in this picture, right? It'll be something. So it'll look something like this. Even in this, there are a lot of classification. M dot to type A, type B. You have a lot of things. Type M is also there. Yeah. So yes, based on this, for example, this is the one. You can see here. Just give me a second. I will just show it to you. Yeah. So your NVMe, right? Based on your what do you tell? Yes, here. This also gives a very clear picture how your normally things how the connection happens to your PC. Okay. So if you look at here, see here. If you look at your any normal drives, right? Traditional drives. Basically, it can be HCI drives, anything. Ultimately, you will have an HCI driver, but you need to have something called as HBA. That is nothing but host bus adapter. You should have a host bus adapter that will translate to something your SATA mechanism. From SATA, it will go to the SATA controller of your device, basically SATA based device, and you'll get the response back. Okay, this is how the normal connection will look like. But if you look at your NVMe subsystem, right, you'll have a NVMe Express driver. Ultimately, the data communication happens by a PCIe, and inside your device, you'll have the controller also. See here, you'll have a NVMe controller, ACI controller. Everything is part of the device itself. Ultimately, so you'll have a building blocks to understand the PCI parts and pass it to the controller. And for controller, once it processes the data, you'll get the response back also. Okay, so this is how your PCI Express SSD would look like, as you see in this particular example. Okay. So now what I want to try here is, this is the, so basically your m dot to NVMe, right, is classified into two things. It's called B key. Okay, where you will have the notch, something like this. If you can see here, there'll be 6 pins available at this side. Okay, there is also called as M key, m dot to NVMe, where you'll have 5 pins at wherever you have the less number of pins, right? If you see 5 pins there, then it's an M key SSD. Okay, M dot to SSD. If you see 6 pins, it is nothing but B key. And you have a combination of both, which is called as M and B key, where you'll have 6 pins and you'll have 5 pins, and you'll have center, you'll have some more pins also. Okay, so based on this, you'll have a lot of things. Okay, so basically, if you look at all these pins, right, whatever pins that is coming out of NVMe, right, it'll have following things. It'll have a NVMe connections, lines for NVMe connection. Okay, then it'll have a lines for your SMBus connection. It'll have a lines for your I2C connection. If there is a UART, you will also get the fetch the UART out of it. Okay, so like this, lot of connection information you will get out of this particular subsystem also at any point of time. Okay, so if you take NVMe subsystem, it will support SMBus, it will support UART, it will support I2C. All the spins will come out of this NVMe subsystem. So that is what I wanted to highlight in this particular subsystem. And if you take any NVMe, right, it supports all of this operating system. For example, it will support your Linux. Okay, it will support your one of the main reason why NVMe is also popular is it has support for all this operating system, and that too in Linux. It is a very stable support at any point of time. Okay, so this is something which I want to understand. Okay, so for example, once your NVMe subsystem is detected by your PCIe, right, there will be an address map that is will be available telling that where is this particular register space been mapped. And if you go to that register address and if you look at it, you'll be able to see all of these registers basically. And there'll be some specific register that is available. See here, there'll be some specific registers that is available, and you can see all of this in this particular points at any point. Okay, so these are all the register sets that is available. You can have a look at it. There will be a lot of registers. Okay, so I will try to explain you how this things really works. For example, if you take NVMe, right, we talked about queue, which can support almost 64K queues. So how this queue works is, you need to add data at one end. Okay, so one end you should be adding a data. Okay, so other end, basically you will have a two pointer called, one is the head pointer and another is the tail pointer. You can configure both of this pointer, telling that initially it will be set to 0, 0. Okay, so based on this, there'll be one point where you have to push the data and you have to increase the head pointer. Okay, so you'll have an head pointer. So head you should not touch basically. Okay, so head is where you need to indicate what is the start of the message. And tail, each time you have to add the data, you have to push the data to the tail. That is something which you need to take care. For example, if it's a circular queue basically. Okay, so this is how your circular queue will look like. If you look at this memory, right, it looks something like this. So thing is, you have to keep adding the data to the tail. So tail will always point to the next free element. So what you have to do is, you should be keeping adding the commands to the tail. So your nvme controller, once you configure your nvme controller telling that which is the head, it will start picking the data from the head, it will process it, and it will get the response back. So now what will happen is, this is a circular queue. At one place you have to be adding the data. In other end, controller will be taking the data and it will be processing at one shot. So this is how this processing will look like. Okay. So what will happen is, so if head is equal to tail, it means that the queue is empty. If head is equal to tail plus 1, that means if tail is already pointing to this particular place, end, it will not point to head is equal to tail. If it points, it means that both are same. In case if tail is pointing to head plus 1, that is nothing but at this location, it means that your queue is full, and then it will not push any and you can't push any command to the queue further down the line. Okay, so this is something which will happen. And even if you take your nvme, right, there'll be two kinds of command queue. One is called as a submission queue, and one is called as a command completion queue. You can tell which queue should be used as a submission queue and which queue should be used as a completion queue. So what will happen is, the concept is something like this. You will have one queue where you'll be submitting the commands, one after the other, you'll be submitting all the commands. Once the controller picks up the data, and you'll have a tail telling that which is free, it will be something like this. For example, initially both will be, head and tail will be pointing to the same place. And once one of the command is moved, tail will move down. And one more command is moved, tail will move down. So like this, tail keeps moving down and down. Once the controller becomes active, it will be picking the data from the head, process it, and move to the next point. It will process it, move to the next point. It will process it and move to the next point. So this is submission queue. This is where the command is available. Now we have one more queue called completion queue, where the controller will give the status of the command execution. What command it executed and how did it, at what status did it execute it. Okay, so did it happen with respect to error, or did it execute successfully? That information you'll be able to see in this particular scenario. Okay, so what will happen is, it'll pick up one of the command from here, it will process it. Once the processing becomes successful, the response will be put into this particular queue again. So like this, what will happen is, each time you get the command, it will be processing it, controller will process it. Once the processing become complete, it will update the completion queue and it will go out. So here in this case, the reader was the controller. So in the completion queue, and writer was the host. Basically, host application which is triggering the action, right? That is the one that is responsible for writing the data to the completion submission queue. But command queue, it becomes opposite. The writer will be your controller. The status will be written by the controller. Your host application will read the command. So basically, what will happen is, you will have the head, and each time you fill the data, the tail keeps increasing. And once the data is read, the tail keeps reading the data and it comes out. So this is how it will happen. So you'll have a command queue and you'll have a completion queue. Okay, so this will be linked between your host. So if you look at it, this is the connection between host and the controller. Host is nothing but your PC side, PCIe host. That is what I'm talking about. Okay, and this is the controller is nothing but your NVMe controller. This is how the overall big picture would look like. Okay, so you take any subsystem, for example, if you take your NVMe controller, right, for in this case this one. So in the PCI subsystem, right, you will have a lot of things connected through the root complex. Root complex is nothing but the first point where your PCI starts. To that, one of the root complex, the NVMe also will be connected. It will have an NVMe controller inbuilt to it, and it will have the SD flash. It will have the SSD, basically NAND flash also available on this to store all the data and do some kind of an analysis. Okay, but your completion queue and storage queue will be available in your somewhere in your PCI memory. There will be a PCI memory that will be associated, that can be accessed by your controller. So what will happen? This command queue can be accessed, since it is part of your NVMe. This memory can be accessed by a PCIe, which means that your host also can access this memory, and even your PCI also can access this memory. So we need to reserve a common memory, PCI memory, which is accessible both by your NVMe drives and even your host also. This is something which you should take care of. Okay, so this is something which you should see. So this is something which you should take care when you're communicating with your NVMe subsystem, as you see in this particular example. Okay, so this is one of the parts, and you can have a look at it. There is a sequence how it happens. Okay, in NVMe controller, there is a concept called ring a doorbell. That is very important. I will tell you what it is. For example, the step is something like this. Whenever host wants to trigger some action, he will create a command and he will put it in the submission queue. And there is one register in an NVMe controller called ring a doorbell. Moment it is ringed, it is an indication telling that there is an information available which controller need to process. So what I will do is I will ring a doorbell. So once I ring a doorbell, controller will get to know that yes, there is something to be processed. Then a controller will try to fetch a data from the command queue. It will execute the command. And then after that, what it will do is controller will write the information to the completion queue. And then your controller will generate an interrupt telling that yes, there is an information now in the command queue, please process it. This is where the interrupt will come into the picture. And after that, your host controller will go to the completion queue, read the data. And after doing this operation, this host controller will ring one more doorbell, completion queue, basically your complete doorbell to indicate that yes, I have read the completion queue information. So the host need to trigger two doorbells. One doorbell to indicate that yes, data is available for processing. One more doorbell to indicate that yes, data was completion response was read successfully. This is the flow how it goes in a NVMe subsystem, and this happens like this at very fast rate always. Okay, it keeps happening like this. If you see here, there will be multiple queues, there will be multiple command queue, there will be multiple IO queues. The data will be coming, it will be processing, and you can perform the action and you can do whatever you want. And you can have any number of host queues, basically it's a submission queue, and you can have any number of completion queue. But in the register, you should tell what command queue, what submission queue will be available for which command queue. That is something which you should understand. Okay. And in NVMe, there are two categories. One is called as an admin data, and one is called as a normal data transaction. Admin data is nothing but whenever you want to control how the NVMe should work. That is called admin action. And for that, there is a dedicated completion queue and submission queue. And there is other commands. For example, in that 64K queues, right? 2 queues will be reserved for admin activity. And the rest of the queues will be used for all the data transfer activity, which you can associate with any core or any thread, and you can perform the action the way you want. Okay, so this is what is very important. You can look at all this thing, that is fine. So basically what I want to stress here is you will be able to issue the command and it will perform the transaction at any point of time. That is very important. Okay, and in NVMe, there is something called a concept called namespace. It's something like your partition details. For example, if you have your NVMe drive, right? Sorry, your normal hard disk, you partition into multiple entry. So which tells that, okay, this is a drive 1, this is drive 2. Like this, you have a concept called namespace in your NVMe. Each namespace will group a certain amount of space for it for working. Okay, so whenever you want to issue the command, you can issue command only to the namespace, so it applicable only to that namespace. Like that also you can do. So you can split and you can do it. For example, you can have a single controller and you can have a single namespace, or you can have a single controller and you can have multiple namespace, and you can have multiple controller and you can have multiple namespace. All these specifications are possible at any point of time, as you see here. Okay. And your command for NVMe structure will look something like this. If you look at this, right? So this is the way how your NVMe structure will look like. For example, let me show you. Yeah. So this is how it look like. You'll have that command. You'll have some bits to indicate what is happening, and you'll have some pointer. For example, this command can't hold the data information because this command is only 15 bytes. Okay. So for example, it's of length only 15 here. That is nothing but your 15 into 4. So much bytes will be available for this operation. But whenever you want to transmit the data, right, you can transmit 64k data or more than that. Okay, to do that, what we do is we put an indication to the pointer telling that where the data is available, where it has to fetch the data from. It's like a linked list. The pointer where the data is available will be available in this command. So the nvme controller can go to that, fetch the data and perform the translation how it wants. Okay, so ultimately this also you can see it. So this is how the data will be stored, okay, in your nvme subsystem. Okay, so what I want to stress here is at this point, whenever you want to transmit the data from nvme into subsystem, it will use this circular queue and it can trigger multiple kind of commands, and that command can perform multiple transactions. That is what we get to know here. Okay, so now if you look at this bug, right, now since you know how the nvme subsystem really works, at least at eye level, okay, so now first thing is you have to, for example, let us assume that you want to perform from translation on nvme. So you can check out if it is available on pcie, and there's a command called sudo nvme list. Even if you run that command, it will list down the nvme controller. Once you have a nvme controller detected, and you can detect it as a normal drive, you can mount that drive, you can flash with some specific file system type, and you can start pushing the data and you can start receiving the data at any point of time. That is possible with respect to this. Okay, so now you can see that somebody has done while doing this operation. Okay, and they see that it is not getting detected anymore. The drive detection is failing, means that the drive itself is not getting detected. So means if you come to your nvme drivers, let me show you the nvme subsystem. This is where you'll find all the nvme code. Okay, so it is classified into following types. Host is the one what we need to refer to. We are not working as an nvme target, we are working as an nvme host. So this is something which you should look at. Okay, so there will be a lot of code that is available. Core is the main code which contains all the starting code of your initialization part. The pci register transport layer registration part you will see here. Okay, so the nvme handling part you will see in this particular scenario. So if you go into this, yeah, you can check out here. There are a lot of parameters that is available, how it should time out, how it should work, a lot of things you'll be able to see here. Okay, so then a lot of activities happening and you register a lot of work queues, how it should happen, and how basically if something fails, how to handle. So all those kind of a code you see here, this is a very big logic. So if any error is happening, how to do it. Okay, so if you are getting some for example, if you want to handle some the command, how to handle the command. So for example, completion request means whenever I get the data completed by the command completion queue, what should the handling look like, that you can see here. Okay, so for example, if you want to put a command to the command queue, what you should do, like that you will see a lot of things that is available in this particular scenario. For example, how do you change the control states? Okay, so for example, if you want to change the control states, how you want to do it. Okay, so you can check out there a lot of code that is related to this. Okay, so you can see a lot of things, but you need to look at the setup things. Setup is a very important part of the code here, and the core is a central logic which contains all the information. For example, if the drive is not getting detected, right, first thing, for the first place, what it will do is it will always come to the init part of the code, where it will set up a lot of work queues. It will create a one more class called nvme, and then it will tell that this belongs to class of type nvme generic. So the moment it finds any drives with nvme subsystem, it will call the pro function of it. So basically what it will do is it will call the pro function of that particular scenario, telling that what should happen. Okay, so now once the probe, once it finds the class of type nvme and the probe, okay, it will call your lot of code. So what will happen is first it will start the controller, but before that it will try to init the controller first thing. So you can see that it is doing a lot of things, and after that it is setting something here, it's allocating a page, it is setting some more environment, it is seeing that everything is in the right state. Okay, so then after that it sets the all the information, and once all those things are well done completely and correctly, and it also sets the interface telling that if the data comes like this, how should be handled, that how should be handled, all the information you'll be able to see here. And then your drive, NVMe drives will be registered, telling that this is a NVMe drive subsystem.
When the
That
probe is when the probe is called, sorry, I'm very disturbing. When the probe is get called in this case.
so, for example, this NVMe is is a PCIe device, right? If you check out here, wait 1 minute. Wait, I will show that connection details once. Yeah, yes, here. See, NVMe is an PCIe device. Okay, so the moment you get connect, there'll be a class that belongs to NVMe subsystem. Okay, so now, for example, if you see this code, right? Wait, not this one. This one I have to call. See here. You'll do a PCI registration. Yes, look at it actually, where you will tell where you'll register the PCI subsystem and date, and you tell that yes, if this particular kind of PCI device comes, you should call the probe. I will just show you that. Just give me a second. Yeah. Yes. Sorry. Again, it jumped off. Just a second. Let me show you. Yeah. Yeah. See here. If you check here, I have registered a PCI driver, and in the probe function, I've called a NVMe probe. When it will be called? When this ID table matches. And what is there in that ID table? If you look at this ID table, right? Look at this ID table. This is your ID table. So what is there in this ID table? If vendor device belongs to Intel, if PCI vendor device belongs to Intel of this particular code, okay, if this matches, or if this particular thing, these are all pointing to the Intel drives, and these are all pointing to the Dell drives, okay, with this particular product ID, or it is pointing to Red Hat also has some QEMU emulators, even if it is belongs to that. Okay, so if your PCI subsystem has any of this IDs available, okay, it will call the probe. Or else the worst cases, it should belong to, if it doesn't match, the highest priority will be given to first. For example, it will always look from this table from first to last. First, whatever first comes first, it will detect first. But if it is not listed here, the last thing what it will do is it will try to detect whether it belongs to device of PCI class, that is nothing but PCI class storage express. That comes under type NVMe express. And moment it finds it, it will get to know that yes, this is the right device, and it will attach to it, and it will call the probe function. Did you get it actually?
I got it. Yeah, thanks. I got it.
Yeah. So this is the information that will be available, and this is the kind of drives that will be supported as you see here. For example, Kingston drives. There are some particular specification also, or else you can also detect based on this thing. So the moment you detect, it will call PCIe probe. So the moment you come to this PCIe probe, right? Basically, what it will do is it will set up all the environment. Okay. So wait, let me open that PCIe probe.
Actually, 1 minute. Just it's the PC. Okay, the PCI subsystem does so, right? So when it does so, when you insert the device at the same time, it does, right? So how the am I right?
See, normally if you take any platform driver, right? So this is also kind of a platform driver only. Okay. So and this is a PCI platform driver. What will happen is you will register, and you will register this only. You're registering the device, and you're telling that if any, basically you're registering, telling that if any device of this type comes attached to this driver. Okay. So the list, I've given a list telling that if this is of this type, this is of this type, this is of this type, call this driver. If any of the device with this particular vendor ID and product ID arrives, it will call this particular probe function.
Just one minute. In one interview, they asked me how they are calling it. We are registering it, but how the subsystem is doing. Like how is the subsystem is doing?
Yes, I will tell you. See, normally when you connect any of the PCI device, right? If you remember, wait, I will tell you. See, whenever you just assume any blank PCI device comes into the picture. Okay. So
Okay.
it will be detected first by the root complex. Root complex will know that something has been attached because of the electrical characteristics. Okay.
Okay.
That's
Yeah.
the first thing. Then after that, arbitration occurs. As per the PCI protocol, right? Arbitration occurs. In this arbitration, it will try to fetch all the details about the NVMe controller, telling that what is your capability, what you can do. So as per the PCI's subsystem, right? It will fetch all the details about it actually. You remember there's a PCI space, right? Actually, in the PCI space, you get a lot of PCI information, right? That is the first information it will try to fetch. And then once it is done, it will also, as a part of arbitration, it will also assign one space to access the register set of this particular device. And it will also allocate some memory regions for this particular device also. Two things it will do as a part of arbitration. Okay. So once that is done, so what will happen is this information, right? We'll see all this activity will be indicated to the PCIe driver. There'll be a PCI Express driver. Okay. So this information will go to that, and all the registration, whatever you're doing here, will be registered to the PCI subsystem actually indirectly.
Okay.
So that is the reason if you see here, right, we are telling that whenever you're registering, right, there are two ways of registering the PCI driver. You can use the PCI calls and register the driver, or else you can call something like this. Wait, let me call it. I don't know why I'm not able to pull down. Yeah, yeah. If you look here, you can also call, there is an init and exit functions here. I'm telling PCI register driver.
Yeah.
That means I'm registering the PCI subsystem. Okay, because PCI is the one who will get to know this device of this capability has come. I'm registering with him, telling that if you find any device of this capability, call me with the PCI core. Okay, so then the PCI core, what it will do, moment it, because that is the one who will get the information. Because as per this picture, right, once the root complex gets the information, that will be triggered back to your PCI core. The PCI core will look at, oh, has anybody registered with me with this capability? If it finds, then it'll go to know that yes, the match has occurred, and it'll go and call the corresponding driver.
Yeah.
So that is what happens in this particular scenario, as you see in this particular case.
Okay.
Okay. So did I answer your question actually?
Yes. Yeah. Okay. Fine.
So this is how it really happens first. Okay. So look at it. I have some more information I can pass you. You should understand this PCIe root complex. So how does it work? How does the arbitration occurs? And how does it communicate? All those things are very important actually.
Okay. Can you give me a source for PCI? There's a PCI protocol also, right? PCI protocol
Yes,
also.
PCI protocol is a standard protocol actually.
Okay, we get. Okay, fine.
You will see PCI is a standard. Okay. But the driver for that you will find in this place. See, if you can find the information for the PCI, you can go and look at the PCI. See here in this you will find PCI. You can go there. You will find all the information there. I mean, no PRs here, PCI. You will find all the PCI stuffs will be present here. See here, all PCI stuffs will be available here. Hot plugging, how to handle that information is available here. Okay. Then after that, if you want to handle the PCIe subsystem, what should be done? That information is available here. So ultimately, each and every code is available in this part of the subsystem, basically, ultimately.
Okay. Oh, everything, right? Even for
Right.
camera, everything is available, right?
Oh, sorry, camera, I didn't get you.
No, I'm just telling that for every kind of driver, there's an example they have given it in this.
Yes. It's not an example. This is a framework.
Okay, fine. Okay.
This is the complete PCIe driver. Okay. For example, if I tell PCI driver underscore register, there'll be a lot of APIs. Ultimately, it'll register with this subsystem only.
Okay.
Okay. So that you'll see it here, and that is how it will detect, and it will also try to tell, okay, there is something that is available. Please take care of it. Okay. This is the main endpoint. That is what I want to stress here. Okay. So is that fine? Did you get it?
Got it. Yeah, fine. Okay.
Yeah. So this is the main thing. Okay. So I think we gone through that before, but it's fine. This is how this thing really works, and this is how it will try to understand. Okay. Yeah. Is this fine? Can I move on?
Yeah. Sorry. Yeah. Yeah. Okay.
No problem. Yeah. So this is what it is. Okay. So now if you look at it, where was I? Just give me a second. Yeah. So basically now if you look at it, you will get all this nvme code. Wait, let me go to that nvme code. Yeah. The first thing is you will get the core is where all your core logic will exist. Okay. But PCI is your transport. The first entry will always occur via the PCI. So what you will do is you will register with subsystem to go, how to play, everything you will mention here, and you will have a probe function also. Because if anything problem occurs, right, it will occur because of this probe. Because probe will have some logic which might affect its behavior. Now, if you look at NVMe probe and see what exactly is doing here, you will get some information. For example, this is the probe function. If you look at here, there are a lot of things that is happening. You're allocating some memory. Then after that, you're allocating some queues. This should not create the problems. And you're getting the device. Then you're setting some driver data here. Then you're getting the device map of your thing. Then you're creating some, what do you tell, some kind of callback work queues, how to handle a different situation. And then based on that, you will have a lot of shortcuts. Basically, crook is nothing but a kind of a shortcuts. Okay, for different kinds, what kind of workaround is required. For example, each NVMe drive from different companies, right, will be developed keeping something in mind. Okay, so at that particular point, even though the protocol is generic, right, they need some kind of tuning somewhere for that to work very efficiently. That tuning information you can control it via this quirks. Basically, this quirks control and tell how the system should behave. So you can set whatever you want. There are a lot of things what you can set. If you can say, if you set it right, ultimately what will happen is everything will be set up here, and then this will call a function called async probe. It will reset your controller. Basically, first time you have to reset your controller, and at the end it will call your async probe. Basically, it will do a lot of resetting action. It will do scanning action. So at the end, you will see that it will come up to your core function. At any point, it will come up to your core function to do all the initialization. Okay. So if you see your core part, you'll see a lot of code related to that, basically how to do things. And you will also see a lot of parameters also. If you want to set some quirks, you can also set from there. And other than that, you can do a lot of other setting. You can set the timeout values, you can set the other things. So if you want to do some kind of fine tuning, right, you can tell and retries. For example, if your controller is not available, it will retry a few times before telling that things are not in control. Okay, so that also you can do here. So retries are also there. Like this, you'll see a lot of things that is available here, because this is the core logic. And then at the end, you will also see the logic related to handling different things. For example, if it is of type admin queue, what to do. If it is not type of admin queue, what to do. All those information you will see at any point of this. Is init control is something what we saw here. So it will set up everything. For example, it will discard the message, it will allocate the ID, it will set up the namespace. Okay, that is the reason you will see it. And after that, it is performing other actions also. It will add some new drivers. So you see a lot of things that will be available because of this particular entity, as you see in this particular scenario. Okay, so what I want to stress here is, with this particular example, we should be able to control our NVMe subsystem. So by looking at this, we'll always get a clear information what exactly is happening at any point of time. So in this particular case, they found that the NVMe drive is not starting, and the NVMe drive was related something to the silicon motion controller. Okay, so now if you see here, right, they debugged and found out that this particular condition was not correct. There is a condition called nvme scr dnr. Okay, so which is there in core.c. If you look at this, I don't know whether it's still there or not. We can look for it. Let's see here. So this is nothing but the error flag. Okay, so this is nothing but kind of a status flag that comes out of your nvme register set to tell how the things are working. So if you look at here, this is the one. Yeah. So this is the one. So when let me check out, I think this is not the correct thing. Just give me a second. Yeah. So something like this. If you look at all those things, right, it will use some condition. Based on that, it will try to find out what is the case, and based on that, it will set a few parameters and it will work. Okay. So this all these things, information will be available by your status register. So the moment you read the status register, right, you will get all this information. That is what you will get. Okay. So here there is an option telling that nvme scr dnr. So this is one of the options that was missing. If you look at this, yeah. So there are So there is something called scdnr command which is pointing to this. Okay. So now by looking at this, and these are all the written code or generic error status, what comes out of your nvme subsystem, as you see in this particular example. Okay. So what was happening in this particular bug was this particular status code was set in such a way that so normally what will happen is if the status, so normally in certain scenario, what will happen is you will get the status register set. So when such thing comes, we have to ignore and continue further down. So we have to ignore and continue. That is one of the important things what we have to do. We have to ignore and we have to continue. But in this case, what was happening was there was some change that was done in between, where the status, because in a particular drive, right, ignoring was not required when the person who merged this code was testing with a certain category of drive where the status change will not occur. Okay. So due to which it was used to work fine. So in that particular drive, it was working fine. But later for this particular drive, whatever we are talking about, which comes out of Silicon Motion, right? There's a chip that is introduced by Silicon Motion. And from that, it can be seen that if case, okay, this particular status changes, so in that particular drive, as per the, if you see here, right, this was the commit. Before they were considering the status bit, and slowly they changed it to reject it because on that particular drive, this was irrelevant. So else what it used to happen was it was checking for this condition because of the status was not changed. And status was not becoming 0, due to which it used to fail. For that reason, this workaround was, or this bug, this fix was done so that it will take care of fixing it and taking the action. So if you look at it, you can check out that this review, this patch contains a lot of information. The information what it contains is who was the author, who fixed it. And normally it is not the case. Whoever might be the author, the guy who will commit this code is somebody else. So that you can check out who's committed this and which commit ID it is available. And if you want to download this alone, this kernel or this particular Linux, this particular patch, you can do that also. And you will also get to know who reported it. This issue was reported by who, for which issue this fix was done, and who and all reviewed it and signed off this particular fix. Means that signing means that who has reviewed and confirmed that yes, this is right to go, or else who have tested it and found out yes, everything is in the right state. So there will be some signing entity and there will be some review, there will be some person who reviews it. And ultimately, once everything is working as per the expectation, they'll push it, this particular code to the main line, as you see in this particular scenario. Okay. So this is something which you should think of as you see in this particular example. Okay. So that is something which you can do in this particular. Yeah. So that is something you should be able to do in this particular case, as you see in this particular scenario. Okay. So based on that, you can see that yes, this issue was detected, identified, and you can figure out. So why I mentioned all this thing is because first thing is you need to understand, if you want to read the register, right, you need to really understand where the registers are available. Where can you get the status register data? So if you want to read this, you need to understand this is part of the PCI subsystem. That is the reason I stressed on the PCI subsystem. And moment you know that this is a PCI device, you should also know that this, but there will be some address where the register will be mapped. And there will also be an address where, so we'll have one address where the register will be mapped. You can go to that register and you can fetch all the information about your status. That is the reason we talked about that. And then that's after getting that information, you should act on that also. So that is the reason I also did a kind of a walkthrough where the source is available, so that we should be able to fix it. So that is how it was done. This bug was proceeded, and they were able to fix this issue, and this is the fix that is available for this particular NVMe issue. So to understand what is this fix and other things, so you should know the basic idea about how the NVMe looks like. So that is the reason I gave an explanation with respect to that particular aspects. Okay, so by this you can check out, and it was also tested and it was also proved that this particular fix was capable of fixing it at any point of time. Okay, so any doubts or questions from your side actually on this?
Can you explain that again, the last one, that what fix it?
Yeah, see here actually, if you look at this fix, right? See, after debugging, see, normally if you remember, right, there are a lot of startup code, and if you see, right, some of the code will reside even in the control code.c also, because there will be a lot of code. Okay, so in that code path, while you're debugging the code flow, whatever I was explaining, right, which is nothing but related to the startup, it was figured out that on that particular NVMe controller, the why it was failing was the status was not becoming 0. Why it didn't become 0? Because reason is, before the status, in some scenarios, the status will be greater than 0. So once you get the status greater than 0, means that there is a failure. But under some situations, this 0, which is, even though there is a error, it doesn't matter as long as this NVMe bit is set. If in the status bit is NVMe SCR is set, even if you get error, you can ignore it, because it is something to do with DNR. You don't need the DNR on this particular controller what was being tested. The controller what was being tested was this one. You can check out that. They given the information also. That is nothing but your J something board, and this is nothing but a silicon motion device, as you see in this particular example. Now it was seen that on this controller, this particular state was becoming false, but as per the datasheet of that controller, it was seen that the status will become NVMe SCR DNR if, and this is the valid thing which we should be able to reject it if this particular bit is set, and then due to some reason, and because if this comes, there's high probability that status, some kind of interaction with the subsystem also will fail. So now what will happen in this scenario is the subsystem has failed because the status was not 0, and because of this DNR. So since we know that this controller will be able to handle DNR, so this will be handled in such a way that okay, so where all the space will be freed. So basically rather than the space, I can tell that once the status bit is available, then the status will be set to 0, indicating that everything is successful. And based on that, all the other things would be taken care of, as you see in this particular example. Okay, so this is one of the example where you'll be doing all these actions. Okay, and that is what you can see here, and that was debugged and found out, and that is the reason this fix was applied at this particular point. Okay, so Vinay, did you get it actually?
Yeah, okay, yeah, got it.
Yeah, so you can look at it. See, if you look at this NVMe specification to get all this information, right? Look at this NVMe specification. Okay, there will be a lot of registers that is available. For example, wait, I will show you the registers that is available. Just give me a second. Not this reset. Wait, I will show you. These are all the commands. I want to show you the register set. 1 minute, NVMe registers. One minute. One minute. Let me see if this is the correct register. This is another register. You can check out here the lot of register that is available. For example, cat register, int ms register, controller status register. So by looking at the status register, right, it will check out whether the DNR is set. Okay. So if the DNR is set on this particular chipset, it is found that it is not required. And because that is a scenario which was mentioned as per that NVMe controller, what was been debugged. So based on that, it was figured out that yes, this is not applicable, and it was taken care as you see in this particular example. Okay. Yeah. So this is one of the thing how it was proceed way how do you proceed and debug it. Okay. So this is at least one thing. Okay. What was done with respect to this bug. Okay.